I welcome you all to this class on abstract algebra. So today we'll be studying this topic, integral domain. So our topic today is integral domain. So in this class I will define what integral domain is and give examples of integral domain and non-examples of integral domain. So basically this class will be the introductory class to this integral domain. Then in our upcoming class we will look at some proofs on this integral domain. But what is an integral domain? So an integral domain is just a commutative ring with identity in which there is no zero divisor. It is a commutative ring with identity in which there is no zero divisor. Let R be a ring. Then R is an integral domain if R is an integral domain if R is commutative. Another one is, the first point is R is commutative. R has identity. The identity of the ring R is noted by 1 and it is different from the additive identity. So the ring must be commutative. For the ring to be an integral domain, the ring must be what? Commutative. The ring must have identity, and that identity is denoted by what? 1. And this identity is called the multiplicative identity, and which is different from what? It is different from the zero identity. The zero identity of a ring is the additive identity. So another thing about the ring is that it has no zero divisors. It has no zero divisor. So in the ring there should not be zero divisor. That is, what does this mean? That is, for all A, B in our ring R with A, B equal to 0, this must imply that A equal to 0 or B equal to 0. Now, in the concept of ring, zero divisors are those elements of the ring which are non-zeros. So the elements of the ring must be non-zero, and if you multiply those two elements of the ring, you are going to get 0. Now for zero divisors, you have A is not 0, B is not 0 in a ring R. So you have a ring R and you have two non-zero elements of that ring, and it happens that AB is equal to what? 0. So this is definition of zero divisor. A zero divisor is a non-zero element of the ring which will multiply another non-zero element of the ring to give you what? 0. The 0 you are seeing here is the zero element of the ring. So, but in this integral domain, there should be no zero divisors, which means if I have two non-zero elements of the ring, if I multiply them, my answer should not be 0. So that if I have A and B in the ring, A times B, if A times B gives you 0, it means that one of them must be 0. So if A times B is 0, it implies that A is 0 or B is 0. So this is a complete definition of an integral domain. So we are going to move into examples of an integral domain. So let's consider examples of an integral domain. The ring, number 1 is the ring of integers. The ring of integers denoted by Z. So the ring of integers is an integral domain. Why is it an integral domain? We know that if we pick two integers, let me say A and B. A and B are integers. For instance, we know that A times B is equals to B times what? A. For instance, 3 and 4 are two integers which we know. And we know that 3 times 4 is equals to 4 times what? 3. So in the ring of integers, we have the commutative law holds there, because A times B is equals to B times A. Then, what if we say that for a ring to be an integral domain, it must be commutative. So the integers, all the elements there are commutative. It must have identity. What is the definition of multiplicative identity? Because the identity here must be a multiplicative identity. Now, in the integer Z, we know that 1 is in Z, right? The integer 1 is in Z. And for all A in Z, for all elements of A in Z, A times 1 is equal to 1 times A, which is equal to A. So the multiplicative identity in integer is what? 1. Because if you use 1 to times any element of the integer, you are going to get back the same element. So A times 1 is equal to A, and 1 times A is equal to A. So the ring of integer is commutative. It has what? Identity, which is a 1. Okay. We say that the ring must be commutative. It must have identity. It shouldn't have a zero divisor. So we know that in integers, we know that if you have A and B elements of the ring of integers, assuming that A and B are two integers, we know that A times B equals to 0 implies A is 0 or B is 0. This we know quite alright in the ring of integers. If you pick two integers, assuming you multiply two integers and you get 0, it means that one of them must be what? 0. That's the only possibility for the product of two integers to be 0. One of them must be 0. So ring of integers Z satisfy all the properties of this integral domain. So the ring of integer is an integral domain. Let's consider another example. The ring of rational numbers, which we can denote as what? Q. The ring of rational numbers Q. Can use similar explanation we use in the ring of integers for this one of rational numbers to check whether it's integral domain or not. So the number 3, we say that ring of integers, ring of rational numbers, the ring of real numbers. The ring of real numbers is an integral domain, because if you multiply the product of any two numbers is commutative. So if you pick any two real numbers, A and B, or let me say X and Y, X times Y is equals to Y times X for all X and Y in the element of real numbers. So the ring of real numbers is commutative, and we know that the element 1 is in the ring of real numbers. So 1 is in the ring of real numbers, and if you do 1 times any element of the real numbers, you get back the same element of the real number. So 1 is the multiplicative identity of R, the set of real numbers. Then it means that the ring of real numbers is commutative. It has multiplicative identity 1. So what of a zero divisor? Does it have a zero divisor? the ring of integers has no zero divisors, because the only time you multiply two elements of real numbers to get zero is if one of them is what? Zero. So the ring of real numbers is an integral domain. So we can talk of the ring of complex numbers. The ring of complex numbers, which you can denote as C. So the ring of complex numbers is an integral domain, just similar to real numbers. Like if you pick any two complex numbers Z1, complex number Z2, Z1 times Z2 is equals to Z2 times Z1 for all Z1, Z2 in the in the ring of complex numbers. Then that's commutativity holds there. So we can think of the identity, the multiplicative identity. Yeah, the multiplicative identity is 1 for the ring of complex numbers. So 1 is in the ring of complex numbers, and 1 times any element z in the complex numbers gives me back that element z in the complex numbers. So it satisfies identity and commutativity. What of zero divisors? We know that complex numbers has no zero divisors. This is because if I pick two elements of the complex numbers z1 and z2, if I multiply z1 and z2 and get 0, it is only possible if and only if either z1 or z2 is 0. So if I multiply two complex numbers z1 and z2 and get 0, it means that z1 must be 0 or z2 must be 0. So the ring of complex numbers is an integral domain. So what of the ring of so let's consider number 5. The ring of integer modulo a prime, which is ZP. So the ring of another example of an integral domain is the ring of integer modulo a prime. So that's Z mod P, where P is a prime number. So we are saying that this is an integral domain. So because all the elements of ZP are inside the integers, all the elements of ZP are also elements of integers. So commutativity holds there, and we know that 1 in ZP, 1 is there because elements of ZP are in this form: 0, 1, 2, dot 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 to P minus 1. So this is how elements of ZP looks like. So it's elements starting from 0 to 1 less than P. So 1 is the multiplicative identity is there. So we think of 0 divisors. So ZP has no 0 divisors. Why doesn't it have 0 divisors? Because if you pick any element A in ZP, if you do the GCD of that element A and P, the answer must be what? 1. P is a prime number. So if I pick any element of this integer mode P, the elements looks like this. So any element I pick there and get the GCD is the same as HCF. If you calculate the HCF of that element and this prime number P, the answer must be 1 because P is a prime, and because of that this element A must be what? This element A must be a unit. As far as this A is not 0, this element A must be a unit, and units cannot be a 0 divisor. Units are not 0 divisors.